Welcome to engineers mindset. So let's say we are given the thrust system on the board as shown, and let us say we are asked to determine the reactions at support A and support D, and also find the force in members F to B using the joint method, and also to cross-check using the section method. Okay, so all we need to do now, of course, find the reactions at this support A and D, and also find the force in members BF using the joint method and the section method of analysis, Truss analysis. Okay. All right. So to do this, first of all, we recognize that at point A we have a pin. That's writing the equilibrium diagram. Okay. So let's plot the free body diagram. F, B, D. Okay. Nothing big. Nothing really big about the FBD. Just bring back the segment or the section the way you see it. This is the thrust system. Okay. All right. So we simply have this, and then we simply have this. Okay. So we have here, and then we have here. Now at point A we have a pin, and for a pin support we always have two reactions for a pin support. One of the reaction is vertical, so this is simply R A Y. So reaction at point A, Y signifies vertical, and then the other reaction is horizontal, so we simply call that RAX. So for a pin support, always we have two reactions, one vertical and the other horizontal. At point C, we have a 2.4 kilonewtons force acting downwards. So we have here 2.4 kilonewtons. This is point C. This is point B. And at point F, we also have a 2.4 kilonewtons force acting downwards. Okay, 2.4 kilonewtons. At point E, we also have a 2.4 kilonewtons horizontal. So we simply have a 2.4 kilonewtons horizontal force. Now, at point D, we have a ruler, and I've always said for a ruler support, we have just one reaction. That reaction must be normal. I've always been saying this, normal or simply what? Perpendicular to the surface of occurrence. So which means this reaction must act at 90 degrees to where the surface it is acting. And at 90 degrees, it means we are going to have this ruler to be what? Horizontal at point D. So this is simply RD. It becomes RDX. So this ruler must act at 90 degrees. As can be seen here, it must be at 90 degrees to where? The surface, which is point D. So it must be at 90 degrees to that surface. So rulers always have what? Their reactions at 90 degrees to the surface where they are acting. Okay, meanwhile, pin always has a vertical and a horizontal reaction where they are acting. Okay, not forgetting, we have here, these heights are 4 meters apart. This is 4 meters. This is 4 meters. This is 3 meters. Yes, this is 3 meters. This is 3 meters apart. Okay, so you simply have this. Okay, let's label now. This is point A, point B, point C. This is point D, this is point E, and this is point F. All right, so this becomes the free body diagram. Okay, so having known the free body diagram now, we can now employ the equilibrium equations to find what? These reactions. Now from equilibrium equation, the first law says summation of the entire force in the x-axis must be equal to 0. That simply says look at the system, the thrust system, which forces are acting in the x direction, sum all of them up and equate them to 0. Now, not forgetting, forces that point to the right are always tend to be what? Positive. Meanwhile, forces that point to the left always tend to be what? Negative. So, left pointed forces are negative, meanwhile, right pointed forces are what? Positive. So, let's get all the horizontal force now and equate to 0. At point A, we have RAS pointing to the right, so this force is positive. We simply pick it out, RAS. Also, at point E, we have 2.4 kilonewtons force pointing to the right, also positive. So we simply pick that out, plus 2.4 kilonewtons. And at point D, we have a horizontal force pointing there to the left. So that force is negative. That's simply what? Minus RDX. And the whole of this is equal to 0. So we can simply what? Send 2.4 over to this side of the equation. And we'll simply have here that RAX minus RDX is now equal to, of course, positive sign crosses and equal to sign becomes negative. So I'll simply have minus 2.4. So simply call this equation 1 because we have two unknowns in that equation, so it becomes impossible for us to solve. So we'll call that equation 1. Okay, so now if we examine this equation for the horizontal, if we examine this equation for the horizontal forces, we find out that we have two unknowns in one equation, which is very impossible for us to solve. So the only way we can be able to crack this is actually by taking what? Considering taking moment. And I always say, if you're taking moment, take moment about a point where we have lots of forces, so that the effect or the moment of these forces about that point becomes zero. At point A, we have two reactions, RAY and RAX. So I can decide to take moment at point A. The moment of these two forces at this point completely becomes zero. Then I can take the moment of every other force at point A. So the very best place to take moment now is at point A. So let's do that. Taking moment at A, take moment at A. So summation of moment at point A is equal to 0. Let's consider clockwise moment to be positive, anti-clockwise to be negative. Okay, so we'll do that now. The moment of these two forces about point A automatically becomes 0 because I'm taking moment at that point. So I will take the moment of this force, 2.4 kilonewtons, about point A. The moment of this force, and every other force on the beam, I have to take the moment about point A. Now, this force is pointing downwards, which means moment of this force will turn about in this direction, which is simply what signified like this. It turns in this direction, take moment about point A. And that direction is clockwise toward our direction. So which means that moment is a positive moment. That's the first thing to know. Secondly, distance it takes this force to get to point A is simply what? 3 meters. That's from C to A, simply 3 meters. So the moment of this force simply becomes 2.4 times 3. So you simply have 2.4 times 3. Next is the moment of this force, 2.4 kilonewtons to at point F down to point A. The same thing is pointing downward, so it's turned all about in this direction, which is also like this. That's clockwise to our direction, so it's positive. And distance it takes this force to get to point A is simply 3 plus 3, which is 6 meters. So I'll simply have plus 2.4 times 6. Next I have now is this 2.4 kilonewtons force. This force is pointing to the right, which means it will turn all about in this direction to take moment at point A. So it goes in this direction. And this is also what? Positive to our direction. That's clockwise. But then again, moment is simply force times the perpendicular distance which the line of action of the force makes to the point of moment. This is the point of moment, point A. I want to take moment of this force. The line of action of this force is simply what? Thus, this is an imaginary line that connects the direction of the force. The place or the distance that makes an angle of 90 degrees to where this point of moment is simply where? Here. This is the distance that makes an angle of 90 degrees to the line of action. This is the line of action of this force. This is the distance that makes an angle of 90 degrees to the point of moment. That distance is simply what? This height from here to this point. And that height is given as what? 4 meters. So the moment of this force is simply what? 2.4 times this height, 4 meters. And then it turns downward like this, so it's clockwise. So we simply have plus 2.4 times 4. Okay. Also, for the reaction at point D, this force is pointing to the left. So which means it will turn all the way about this direction. It turns all the way about this direction, which means its moment is simply what? In this direction. That's simply anti-clockwise. It is anti-clockwise toward our direction. And anti-clockwise moment is simply what? We said, let anti-clockwise moment be negative. Okay. And again, the distance that makes an angle of 90 degrees to the point of A with the line of action of the force. First of all, this force is horizontal, so the line of action of that force is simply what? In this direction. You have this. Distance that makes an angle of 90 degrees to this point of moment is simply from here to this point. This is 90 degrees to the line of action of the force. This is simply the distance that makes an angle, the angle of 90 degrees to the line of action of that force. That distance is simply what? This height. Simply 4 plus 4, and that's 8. So the moment of that force simply becomes minus, because it's anti-clockwise, RDX times 8. And the whole of this is equal to 0. So you have that. So let's now evaluate and see. We have here 2.4 times 3. That gives us 7.2. Okay, plus 2.4 times 6. That gives us 14.4 plus 2.4 times 4. That gives us 9.6. Okay, minus 8 RDX equals 0. So let's evaluate now. 7.2 plus 14.4 plus 9.6. We simply have that to be 31.2 minus 8 RDX, and this is equal to 0. So let's send minus 8 RDX over to this side of the equation. We simply have 31.2 is now equal to 8 RDX. So to make reaction at point D subject, simply divide both sides by 8. So this simply implies that RDX is now equal to 31.2 all over 8, and therefore RDX is equal to, that gives us 3.9 kilonewton. All right, so that's the first question. First question says determine reactions at A and at point D. So obtain reaction at D. That gives us that reaction 3.9 kilonewtons. So if you've known the reaction at D, all you need to do is simply what, substitute into the what, equation 1 to find horizontal reaction at point A, which is RAS. So we simply substitute that value into what, equation 1. Let's do that now and see. Okay, so substitute RDX into equation 1. If we do that, from equation 1 we have RAX. This is simply RAX plus, okay, minus RDS. So simply minus RDS now give us 3.9. So minus 3.9 is now equal to, here we have minus 2.4 minus 2.4. So we simply send minus 3.9 over to this side of the equation. Negative sign crosses an equal to sign becomes positive. So you have RAX to now be equal to, we simply have here now 3.9 minus 2.4, because we have minus 2.4 here. And of course, 3.9 minus 2.4 will simply give us that RAX is now equal to, so that simply gives us 1.5 kilonewtons. So the horizontal force at point A has been found. RAS is 1.5 kilonewtons. So we've obtained all the horizontal components. Next is now to employ the second equilibrium law. This was the first, summation f of x. Now we'll now obtain the second, we now apply the second equilibrium law, summation f of y equals 0, which means sum all the vertical forces and equate them to 0. So let's do that now and see. So applying the second equilibrium law, summation of vertical forces, summation f of y is equal to 0. So we always consider vertically upward force to be positive and downward forces to be negative. Okay, so if we do that, let's start now. At point A, we have RAY pointing upward, so this reaction is positive. So simply put that RAY. At point C, we have 2.4 kilonewtons force acting downward, so it's negative, minus 2.4. At point F, we also have 2.4 kilonewtons force acting downward, so it's negative, minus 2.4. Okay, so those are the only vertical forces we have here. The rest are horizontal forces. This is horizontal, this is horizontal, this is also horizontal. So the whole of this is simply equal to 0. So we have here RAY minus 2.4 minus 2.4 gives us minus 4.8 is equal to 0. So we simply send minus 4.8 over to this side of the equation. Negative sign crosses an equal to sign becomes positive. So that simply implies that the reaction at point A, Y, is simply what? 4.8 kilonewtons. So the first part of the question is answered. Determine the reactions of all the forces of all the unknown supports, okay, at point A and at point D, which we've done. We found RAX, RAY, and RDS. Those are done, okay? The next question says we should find the force in member BF using joint method and section method to cross-check the answer. Okay, so let's use joint method first. Let's start with joint method. And I've always said if you're employing the joint method, start with the joint that has with the list. Start with the joint that has the list of unknowns. I always say that the number of members that makes up a joint gives us the number of the unknown at that joint. At joint A, we have two members from A to B and from A to C. So it means we have actually what two unknowns here. But at joint F, we have three unknowns because we have about F to E member F to E, we have member F to B, we have member F to C. That's like three members, which means we have three unknowns. At joint B, we have this member 1, 2, 3, 4, 5. So that's about five unknowns. So the number of member in each joint tells us the number of unknown in that joint. And if you want to start with the member or the joint that has least unknown. And again, also, if you're going, don't start solving towards or don't start solving against what you're not asked for. Let's solve towards what we're asked for. We're asked to find forces in members BF. So, which means if I consider this joint A, I have to start solving from joint A at least relative to where getting along where BF, so that I can minimize the workload of what solving for each of these joints before getting to F, B, or BF. Okay. So we have to work with joint A. Joint A has list of unknown. After joint A, the next joint close to BF is joint C. Okay, if I obtain joint C and then I can now pick a joint F, knowing that BF is same as FB, then I can now what solve. So I have to start with joint A. Let's start with joint A using joint method. Okay, let me put down these reactions now. Okay, so we had RAY. RAY is 4.8 kilonewtons. Let's get it down. 4.8 kilonewtons. Okay, we had RAS. Let's get this off. So we had RAS, and RAS gave us 1.5 kilonewtons. Okay, and then we had RDS. This gave us 3.9 kilonewtons. So I can take all this off. Okay, so consider joint A. Consider joint A. So what we have at joint A is simply this. We have this and we have this. So this is joint A. We have a horizontal force here, not forgetting. We also have a vertical force here, not forgetting. Okay. And the force, horizontal force is simply 1.5 kilonewtons. We have here 1.5 kilonewtons. This is joint A. And the vertical force is simply 4.8 kilonewtons. So we have 4.8 kilonewtons. Okay. So I said whenever you consider the joint method, this member A down to member B, there is always a force. According to the theory of Truss analysis, it says that each member of a truss system carries two equal but opposite forces in the members. So the two forces could be, let's say we have A and B. We have these forces could either be in tension. That means this force is also in tension. They could be pulling out from the joints. So the two of them are pulling out from the joint. So they are in tension, but they are what? Equal in magnitude. So this is F at joint A relative to B. This is F now at joint B relative to what? A. They are equal in magnitude, but they are what? Opposite in direction, as can be seen here. So this is for what? A condition of tension. If it is in compression, that's A, that means the force is pulling into the joint. It means at joint B, this force will also pull into the joint. Still the same thing. This is force at joint A relative to B. This is also force at joint B relative to A. The two forces are equal, but they are what? Opposite in direction. So that is every force member or every member in the truss system carries two equal but opposite forces. We don't know the direction of the force, so we are the one to what? Assume the direction of the force. Okay, so since this is joint A, let me now assume that the force moving relative to B, because this is joint A and this is joint B, let's say this force moving relative to B is what? A tensile force, which means this force must be going out of the joint. So we simply have this, a tensile force. So we'll call this force, since I'm at joint A relative to where? B. Same thing happens here. Since I'm at joint A and this is joint C, this is A to C, I will also assume a direction for that force. Let me also assume that this force is what? Tensile. That means it pulls out of the joint. So we simply have F at joint A relative towards C. That this force is moving from joint A down towards point C. Okay, so that is it. So I've always said if you assume a direction and you obtain a negative value, it only means that the direction you assumed was what? Wrong, not your answer. Your answer will always remain correct. Okay, so if we do this now, if I now draw an imaginary line, let's say I draw an imaginary line here, I will now find out that this is now what? A two force system. This shows my y direction. So this can also show my what? X direction. So this is now what? A two force system. So which means this force FAB is actually inclined to an angle, to the horizontal or to the vertical. So all I need to do is what? Find these angles, either horizontal or vertical. Find those angles. To do that is simple. If here is theta, and then I have this height is given as 4 meters, and I have this base is given as 3 meters. It means I can find this angle using my what? Trigonometry. Okay. All right, so from trigonometry I can find that tan theta is simply what? Opposite is the side facing the angle, and this is simply what? 4. That's this height. Opposite all over adjacent. Adjacent is the side backing the angle, which is what? 3. So we simply have 4 all over 3. So tan theta is actually 4 over 3 is 1.3333. Therefore, theta is simply what? The tan inverse of 1.3333. Okay, which means that angle theta is simply 53 degrees. So it means this angle is known, 53 degrees. So therefore, the angle here is simply 53 degrees. And if here is 53 degrees, it means I can find here, because angle on a quadrant is 90. So if here is 53, it means this angle is simply what? 37 degrees. So having known this now, all I need to do is to what? Resolve this force FAB into what? Vertical and horizontal components, because this force is inclined to an angle horizontally and vertically. So all I need to do is to resolve the force to what? Horizontal and vertical components. And to do that is simple. I said, hold the tip of the arrow of the force. If I want to resolve this force now horizontally, this is the horizontal line. Hold the tip of the arrow of the force. Pull the force till it meets the horizontal line. If it meets the horizontal line, observe two things. First, where would the direction of this arrow point? That's the first thing. Secondly, which angle does this force passes through? The angle this force passes through, multiply that force by the cosine of the angle it passes through. So if I hold this force and pull it till it meets the horizontal line, let me do that free body diagram here because of here is already occupied. Okay, so if I pull this force to meet the horizontal line, this force points where? To the right. It still points to the right because this arrow will still point where? To the right. So this force points to the right. And again, it passes through what? This angle, 35, sorry. And again, it passes through this angle, 53 degrees. So if it passes through this angle 53, all you need to do is simply multiply this force by cosine of the angle it passes through. That gives you the value of the horizontal component of this force. So I will simply have that force to be F A B cos 53, cosine of the angle it passes through. So this is the horizontal component of this force. Next is to resolve this force where? Vertically. Still the same principle. Hold the tip of the arrow of the force, pull it till it meets the vertical line. Observe the direction. If I pull this force to meet the vertical line, it still points upwards. So I'll have this force pointing upwards. Okay, I'll have this force pointing upwards if I pull it to meet this vertical line. And again, observe which angle did it pass through. This case, it moved all the way from here to this point, covering this angle 35 degrees. Covering this angle 37 degrees Celsius. So always multiply the force to where? The cosine of the angle it passes through. So I will simply have FAB cos 37. That becomes the vertical component of that force. So having done this now, it's simple from here. The next thing to do is to employ your equilibrium law. Okay, so from equilibrium law, summation of f of x, summation of horizontal forces are equal to 0. Not forgetting, forces that point to the right, positive, forces that point to the left, negative. So sum all the horizontal force here and equate to 0. Now we have 1.5 kilonewtons pointing to the right, so this force is positive. Pick it out, 1.5. Next, we have FAC pointing to the right, so it's positive, plus FAC. And next, we have, when we resolve this force FAB, we had it here, it became FAB cos 53, pointing to the right as well, so it's positive. Simply plus FAB cos 53. The whole of this is equal to 0. So those are the only horizontal force we have on this system or at that joint. So the whole of this is equal to 0. Okay. So we can find the value of cos 53. So we have here 1.5 plus FAC plus F. Okay. Now cos 53 is approximately 0.60. So simply 0.6 FAB equals 0. So let's simply send 1.5 over to this side. Positive sign crosses an equal to sign becomes negative. So I'll simply have FAC, okay, plus 0.6 FAB equals minus 1.5. Simply call this equation 1 because we have two unknowns in that equation. So we simply call that equation 1, okay? All right, so next is to what? Take the second equilibrium law, summation of vertical force, and equate them to 0. So summation f of y for that same joint is equal to 0. Consider vertically upward forces as positive, downward forces as negative. So you have that. All right, so on this joint, we have 4.8 kilonewtons force pointing upward, so it's positive. So simply put it down, 4.8. Okay, also, when we resolve this force FAB, here it pointed upward, so it's also positive, and the value is simply FAB cos 37. So these are the only two vertical forces we have on this plane or this joint. So simply plus FAB cos 37, and this is actually equal to 0. Okay, so let's simply send 4.8 over here. We simply have FAB cos 37 is now equal to positive sign crosses an equal to sign becomes negative. That's simply minus 4.8. And therefore, to make FA the subject, divide through by cos 37. This implies that FAB is simply minus 4.8 all over cos 37. Let's get the value now. That gives us approximately FAB equals minus 6.0 kilo newtons. So this actually implies that FAB, so take note, we assume tension for FAB. We said let the force between joint A relative to B be tension, that is, let the force be pulling out of the joint. And we obtained negative. It doesn't mean we are wrong. It only means that the direction we assumed was actually what? Wrong. That the main direction of the force in that member is supposed to be what? Compression. So it should be pulling inwards to the joint. So it simply means here FAB is simply what? 6 kilo Newton C. C here stands for what? Compression, which shows that this force is actually what? A compressive force. So that gives us the force in member A to B. So if we know that force, we simply substitute into equation 1 to find FAC. So putting the value of FAB into equation 1, okay? Substitute FAB, okay, into 1. So if we do that, we simply have here FAC plus 0.6 is simply FAC plus 0.6 in place of FAB. FAB gave us minus 6, not forgetting. So minus 6, and that's equal to minus 1.5. That's equal to minus 1.5. Okay, so FAC. Okay, so 0.6 multiplied by minus 6 gives us minus 3.6, and that's equal to minus 1.5. So simply said minus 3.6 over here. Negative sign crosses an equal to sign becomes positive. We simply have FAC is now equal to 3.6 minus 1.5. So this simply implies that the force in member A relative to C is now equal to 3.6 minus 1.5. That's simply 2.1 kilonewtons. And we assume tension for that same force. We said let the force in that member be tension, and we obtain positive value. So it means truly the direction is correct. So direction of that member is actually what? In tension. So TAC of force in member AC is simply 2.1 kilonewtons in tension. Okay. Now, having known the force in this member AC, it now draws us closer to where? B. So the next thing I'll do now is I can now consider joint C, because considering joint C now, I already know the force in member C to A. You see the same thing as force in member A to C. These two forces are equal but opposite in direction. So the two forces are the same. So at joint C now, I have just two unknowns, C to B and then C to F. So I can find, and if I obtain C to F, it draws me again one step closer to where? FB. Okay, so all I need to do now is now consider joint C, because joint C draws me step closer to what? B and F. Okay, so let's consider now joint C. Okay, so consider joint C. At joint C, we simply have here, okay, this is joint C. We have a downward force there of 2.4 kilonewtons. Now, this is joint C. Okay, we also have okay, now there's a member from C to F. We have member CF. We don't know the force in that member. Let's simply call that force also. Let's assume tension. So this is force at joint C relative to what? F. So FCF, force at joint C relative to F. So we are simply calling that force a tensile force that it is pulling out. You can still call it a compressive force. You will not be wrong at the end of the day. Okay. Now, already the first member between AC and CA is the same thing. I've always said FAC is equal to FCA. So these two forces are equal. Now, the redirection is simply what? Tension. FAC here, the value simply gave us what? 2.1 kilonewtons. And it says that the tension we assumed was correct. So which means the first member should be pulling out of the joint, not into the joint. If he pulls out of the joint, it is in tension. But if he pulls towards the joint or into the joint, it's in compression. So we assume tension and we had positive. So which means it's correct. So it simply means that at this joint, relative to C, this force is also what? Pulling out is a tensile force. And this is simply F at joint C relative to A. The value was known as what? 2.1 kilonewtons. We know that. Then we have member C to B. Also, there's a force in this member. We don't know the direction. So we also assume, I will also assume tension. So any direction you choose, you also obtain accurate answer. This is joint C. So let's also assume that this force is pulling out. So this is force at joint C relative to B. So notice now that we have just two unknowns here, FCB and FCF. We have two unknowns, so it becomes easier for us to solve. First thing to do, also employ your what? Always employ your equilibrium equation. So summation of F of X, summation of horizontal forces, all is equal to what? 0. So we sum all the horizontal force and equate them to 0. The horizontal forces we have here is simply what? FCA, 2.1 kilonewtons. Remember, this force is pointing to the left. Don't forget, when the force point to the right is positive, once the force point to the left is negative. So I have 2.1 kilonewtons pointing to the left, so it's negative. So simply minus 2.1. I have FCF pointing to the right, so it's positive, plus FCF. And the whole of this is 0 because these are the only two horizontal forces we have on this system. If that's the case, then simply send minus 2.1 over to this side of the equation. That simply means that the force at joint C relative to F is still equal to 2.1 kilonewtons. Remember, when negative sign crosses an equal to sign, it becomes positive. So we assume tension for this force and we're also obtaining positive. So it means the redirection is also what? In tension. So it's correct. The direction assumed was correct. So the first member C to F is in tension. Also, next equilibrium law, summation F of Y is equal to 0. Consider vertically upward force as positive, while downward forces as negative. So we have here FCB pointing upward, so it's positive. Simply FCB. Then we have 2.4 kilonewtons pointing downwards here, so it's negative, minus 2.4. So these are the only two vertical forces we have on this system. Equate this simply what? To 0. So to make FCB subject, simply say minus 2.4 over here. This simply implies that FCB is now equal to negative sign, constant equal to sign becomes positive. So we simply have 2.4 kilonewton. So since this is positive, we assume tension for FCB and we are obtaining positive. It means the redirection is simply what? Tension, which is actually what? Accurate. So we have that for FCB. Okay, so having found these reactions now, it draws us now closer to what? Joint F. Now we can consider joint F because we have known reaction from C to F. It means now the only reactions we don't know here now becomes Fe and Fb. Meanwhile, the question says we should find Fb. So we have not now know what this reaction, so it becomes easier for us to pick out this joint, knowing that we just have what? Two unknowns to find. Okay, so we can now pick this joint because this reaction that is known now makes the work easier for us than solving before from this joint. Okay, so it makes it easier for us. Now we can now consider joint F. Let's consider joint F. All right, so consider joint F. So if we consider this joint now, this is what we have here. Okay. All right, so this is all we have at joint F, which is this joint. We have a 2.4 kilonewtons force acting downwards here. So label that 2.4 kilonewtons. Okay. All right. The force in members F to C will obtain that value here. FAC. Sorry, the force in members F to C, yes, will obtain that value here. FCF. Okay, we obtain FCF here to be what? 2.1 kilonewtons tension. So which means that force is actually pulling out of the joints. So we already obtained this force. FCF is same as FFC, not forgetting. Okay, FCF is also equal to FFC. The two forces are equal but opposite in direction. So it is tension, which means if this is joint C and this is joint F, this force is in tension. That means it is pulling out of the joints. This is also pulling out of the joints. They are equal in magnitude but opposite in direction. So we simply have that this force is pulling out of the joint. This is joint F. This force is pulling out of the joints. And we know the value. The value is simply 2.1 kilonewtons. FCF here. Okay, so F, this is now force at joint F relative to C is still the same thing as FCF, which is simply 2.1 kilonewtons. Is equal. Now, this force relates to what? Member F to where? B. This is member F to B. So which means that's where the question lies. The question says we should find the force in members where F to B or B to F is still the same thing. Okay, so let's now assume tension. Let's assume that this force is pulling out of the joint. So it is pulling out. This is force in member F relative to B. That's where the question is. That's what they are asking us to find. Okay, let's also assume this is also joint F relative to where? E. So let's also assume tension for this force. That this force is pulling out. So force in joint F relative to what? A. Okay, so we'll have this. So if, as always, if I draw an imaginary line here, draw this. This force is actually what? It shows that this is actually a two-force system. This is my positive X. This is my positive Y. And of course, this negative X and this is what? Negative Y. So which means this force relative to FB, member F and B, is actually what? Inclined to an angle to the horizontal or to the vertical. So we need to obtain what these angles are. To do that is simple. Let's come here. This is the angle theta. Okay, of course, this is corresponding angle. As can be seen here, this angle is corresponding to this. So it means these two angles are equal. But let's also prove it. This height is given as 4 meters. So tan theta is simply opposite, which is 4, all over adjacent, which is 3. And you can see that here, 4 all over 3. If you do that, you still obtain this angle to be what? 53 degrees. So this is corresponding angle. Okay, they are equal. When angles correspond, the values are equal. So the angle here is also 53 degrees. So which means the angle here is 53 degrees. So if here is 53, of course, here will be 37 degrees. Okay. So all we need to do is simply what? Resolve this force to vertical and horizontal components. Resolve this force to vertical since it's inclined. Resolve it to vertical and horizontal components. To do that is easy. I always say, if you want to resolve now to horizontal, hold the tip of the arrow of the force, pull it to meet the horizontal line. Watch the direction of the arrow, very, very necessary. If I pull this force to meet the horizontal line, this arrow points to the left. This arrow now points to the left. If this force pulls to the horizontal line, this arrow points to the left. So I will simply have something like this. The force points to the left. And then observe the angle it passes through. If I pull this force to meet the horizontal line, it passes through this angle, 53 degrees. So I simply say multiply the force by the cosine of the angle it passes through. That gives you the horizontal component of that force. So you simply have here to be FB cos 53 because it passes through this angle 53 degrees and then it points to the left. Okay. Also, resolving this force now vertically, hold the tip of the arrow of the force, pull the force to meet the vertical line, observe the direction of the arrow. If I pull this force to meet the vertical line, this force points vertically upwards. The arrow points upwards, so which means, okay, it points upwards, and again, it passes through which angle? 37 degrees, not forgetting. So I simply have this force pointing upwards. Let me keep it here. This force points upwards and it passes through what? This angle, 37 degrees. So multiply by cosine of the angle. This is simply FB cos 37. So I have this. So since it's the only force that is inclined, that's all. So all we need to do now is employ our equilibrium equation. First, summation of forces in the x-axis is equal to 0. So always, forces that point to the right is positive, forces that point to the left, negative. So sum all the horizontal forces and equate them to 0. I have here FFB cos 53 pointing to the left, so it's negative. So put that down, minus FFB cos 53. I also have here 2.1 kilonewtons pointing to the left, so it's negative. You put that down, minus 2.1. I also have, okay, so those are the only horizontal forces we have on this system. Yes, that's the only horizontal force. So the whole of this is simply equal to 0. Okay, so here I can simply send minus 2.1 over to this side of the equation. I will simply have minus FB cos 53 is now equal to negative sign constant equal to sign becomes positive. I simply have 2.1. So to make FF the subject, divide both sides by what? Minus cos 53. So this simply implies that FFB is simply 2.1 divided by minus cos 53. So this actually implies that the force in joint AB, that the force in joint in members FB, which is FFB, is now equal to 2.1 divided minus cos 53. That gives us minus 3.5 kilonewtons. Okay. Now we assumed this force in that member FFB to be what? In tension, and we are obtaining negative sign. It only means that the force in that member is not supposed to be what? In tension. It's actually supposed to be in compression. So this simply implies that force in member FFB is actually 3.5 kilonewtons C for compression. So it's actually what? A compressive force that exists in that member. So that is the equation. Question says we should find the force in members FB, which we found using joint method.